Yeah, okay. So this is our third week of this live sessions going on. I'm your NPTEL TA. Your TAs for this course will be main TAs will be different. They will be assigned by the institute or the professor who is conducting this course online on the NPTEL website, and the lectures are already posted on the website. As I already gave the introduction and the method by which I adopt in solving the numericals and all the things in lecture week 1 and week 2. I have uploaded those on my YouTube channel, and I hope NPTEL team has shared those links with you. I suggest all of you to go through those lectures, and then it will be easy for you to connect those lectures with the lecture that I will be presenting today. So finite element method, I already gave the introduction in those two lectures, wherein we started with the finite element method, basic finite element method, what it is and why it is necessary. And after that, I carried I tried to make you understand some of the approximate methods that are there in solving differential equations or the boundary value problems, to be precise, because all of the problems are boundary value problems. Because if you see in all the problems, we have some boundary conditions given already, and then we solve the differential equation. So this method is all about that thing. So if we see in the week 2, we ended here solving a numerical on approximate methods using Gillarkin method. Then Gillarkin method, in today's class, we will be continuing with the another method, that is variational method. I have shown you here what are the two types of methods. One is weighted residual methods, in which all the methods came, least square method, then one more collocation method, and then it was Gillarkin method. Now today we are going to deal with these variational methods. Okay, we're going to study these variational methods. One second, someone is joining. Okay, so continuing with the variational method, like let me give a brief recap for the boundary value problem. So, for example, what we did in the last lecture is that, for example, we had any governing differential equation or a boundary value problem in which D was a differential operator. It was acting on some primary function u of x, plus there was some other forcing function f of x is equal to 0. I told you that we assume some solution for u of x, or approximate the solution initially, which is in terms of some constants, polynomial function like a naught plus a1 x plus a2 x square and so on. Then when we put this function back into this differential equation, we get some residual. That is because this is an approximate solution, so it will not be exactly satisfying this equation. That's why we will not get this equation equal to 0. So we will be getting something like this. For example, if I put this equal to f of x, then I substitute this solution into this differential equation back, d of f of x, I told this in last class, plus capital F of x, we will be getting some residual. That is the error there. Okay, let me see how I denoted it in last class to maintain the consistency. Okay, no, I denoted it by e. Okay, I denoted it with e. So I got the error e. So this was all the things that we did in last class. I hope you saw the video there. Now, in variational method, what we do is that we take the advantage of the variation of a function that is introduced in the this approximate solution. So today we are starting with variational method. Can anyone please confirm me that am I audible and is slides visible to you people?
Yes, you're audible
Okay, thank you.
and slides are visible. But I would also like to add that earlier class there was some technical issue because of which access was not like we were not able to join the session. Like some of us were not able to join the session.
Okay, last two classes, I think I was having a little bit of misunderstanding regarding the slot timing. I contacted them in the different slots, so I
Oh, is it? Okay, okay,
or
okay.
later I got to know that my slot is about 3 to 4 for the class and then 4 to 5 the doubts. So today
Okay, okay.
I will be contacted to 3 to 4.
So
If you
now
are
it will be the
interested,
same time then, right?
if you are interested in those two lectures, they are already posted on this my YouTube channel, and the links have been shared with you already.
Okay,
Full,
I will have a look. Yeah, means I
okay,
saw that some link came, but I was not able to see.
yeah,
That.
full
Yeah.
class is available there, both two
Okay, okay,
lectures.
sure. Yeah, thank you.
Okay,
Thank you.
okay. So today is the variational method. This method is also known as Rayleigh-Ritz method. Okay, Rayleigh-Ritz method. Okay. So I want to mention here one thing. I have been doing these NPTEL classes from last 2 years, where I have taught structural analysis, RCC, and other undergraduate courses. And my technique is like that: I first give a brief concept regarding that topic, and then solve the full numerical problem in the same class to give you a full idea about what is happening there. Okay. I hope all of you people are comfortable with this. So, like, if there is this variational method today, I will give brief background behind the variational method or the Rayleigh-Ritz method. Then I'll be solving numerical regarding this. So, today's variational method or Rayleigh-Ritz method. In variational method, I told you we already assume first the approximate solution. That is, for example, we assume u of x to be equal to a naught plus a1x plus a2x square. Because we assumed this solution in the previous problem, we can have a look on that. So what is our aim is that when we put this approximate solution in a differential equation, the error that we get, that should be minimum. That is our aim at the all. That error will be minimum when we will minimize that error with respect to these unknown constants a naught, a1, and a2. So all of this is a minimization problem. Like in the finite element method that we will be studying in the coming classes or the in coming weeks, we will be developing a base for those that finite element method, how it came to known. Actually, finite element method is also a technique of minimizing the error into the approximate solution that we assume, and then we put it in our differential equation. So it is like you have some unknown constants. You have to choose those unknown constants in such a way that the approximate solution that we assume, it should be as close to the exact solution as possible. So this is the basic idea behind it. So what we do is that we use variational calculus, wherein we write u bar of x to be equal to, we induce very small change in these unknown constants. Like a naught, we induce small change delta a naught. Okay, very small change. And similarly in a1 plus delta a1, and x is there already. And in a2, I also induce delta a2, very small change in the unknown constants x square. And then I will see the what is the change in this approximate solution or approximate function delta u of x. It will be obviously equal to the new approximate solution that I got after inducing the small change in the unknown constants minus the original function u of x. If I take the subtraction of these two functions, you will get to know that I will get these things. I get delta A naught plus I will get delta A1x plus delta A2x square. You keep this thing in mind because we will be using it in a couple of few minutes, okay? Like this one. Continue. Then what I see that is this delta U of x, I will say it is variation in approximate approximate solution, okay? So we saw that how we calculated the variation in the approximate solution delta u of x. Same variation we can have in the other functions, like we have other functions or the variation in the differential operators as well, such as we have the first derivative of u or we have the square of u. We can write the similar expressions for them. For example, for other functions, how we can write variation functions, we can write the variation as, for example, we have a function f of x is equal to, it is same approximate solution, we are taking its derivative, that is d by d du by dx. U of u is a function of x. So how we can write its variation? We have to write variation of f of x is equal to variation of du by dx, okay? Du by dx like this. So I already told you how we write this as, it is a difference between du bar by dx minus d original u by dx. Okay, so if we see that, if we take the derivative of this like this, we have to take the derivative of this with respect to x. We will get delta a1 plus delta a2 to delta a2 x. Okay, we have to take the derivative of this one. So derivative of this, delta a naught is constant, so it will be 0. Delta a1 times x will be delta a1 plus delta a2 x square will be 2 delta a2 x. Okay, I hope that you got this point. Okay, so the differential will be delta a1 plus 2 delta a2 x. So why I'm requiring its derivative? Because our original boundary value problem is containing the derivatives of a function. So obviously I will be requiring the derivative of a variation of the function as well. Okay. So one more function, for example, we have another function g of x to be equal to u square of x. If we have to take the variation of this function, we will take variation of g of x is equal to variation of u square of x. Okay, how we will write it as, we will again write u bar square of x minus u of x square. Same, we have to take the square of that function. Then how we will get, it's the simple thing, like you have to do the square of this function, square of this function, then subtract again, you will get the variation of u square of x. These were the simple things like this. Okay, then what we have to do is, like we have to go to our, we will require these quantities as well, as I once again I will write u to be equal to a naught plus a1x plus a2x square. You please also note these quantities we will be requiring in subsequent slides. Du by dou a naught, differential of u with respect to a naught, it is obviously equal to 1. With respect to a1, dou u by dou a1, it will be equal to x, and dou u by dou a2, it, it is equal to x square. I will be requiring it in solving the numerical further, okay? So that's why I calculated these beforehand. So we calculated this, and one more thing, variation we calculated, like variation of u to be equal to delta a naught plus uh, uh, delta a1x, delta a1x plus delta a2x square. If you see that, if I put 1 here, multiply by 1 here, it will not change the function. So if you see that delta 1 will be equal to, like, sorry, 1 is equal to this, 1 is equal to this dou u by dou a naught, this x is equal to dou u by dou a1, and this x square is equal to dou u by dou a2. So I can write the variation of u in another formulation like this. Variation of u is equal to partial derivative of u with respect to first coefficient a naught times delta a naught. Isn't it same? Delta a naught, and in place of 1 I wrote dou u by dou a naught. Similarly, in other places I can write dou u by dou a1 times delta a1 plus dou u by dou a2 delta a2. Isn't it so easy? So I can write the different variation of a function like this. Okay. So if you remember, I hope you remember this expression. If you remember your differential calculus, that this expression closely resembles to the total differential of a function. Okay. So we can write thus variation of a function is equivalent to the total differential of a function. Okay, because you know if u was some function, sorry, we are writing u everywhere. From differential calculus course, you may be knowing that if f was some function and it is some g of depends upon the variables x comma y comma z, then we write the total differential df to be equal to partial derivative dou g by partial derivative with respect to first variable dou x dx plus dou g by with second variable dou y dy plus dou g by dou z third variable dz. Same is the function here because a naught, a1, and a2 are the variables. Although they are constants in an approximate solution, but their value is to be determined. So we have to minimize their value. We have to choose their value in such a way so that error is minimum. So if you clearly see that how in variation calculus, variation of a function is exactly equal to the total differential of the function. So in general form, we can write the variation of a function to be equal to variation of a function in general form. Okay, general form, we can write the variation of a function to be equal to partial derivative with respect to first unknown constant a naught d a naught. Sorry, here d is here we don't have differential, we have variation. Okay, delta a naught plus up to, if we have n unknown constants, dou u by dou an delta an. Okay, I hope this thing is clear to you. Okay, then now moving forward, we have some identities that we will be using. Like if we have to find the variation, some identities. Okay, like we have basic identities like a plus b ka whole square is equal to a square plus b square. Same, we have the identities for variation of a function as well. So we have these identities. Okay, for example, you have to take the variation of a function which is raised to power some n. Variation of u with raised to power n. Actually it is equal to same the derivative you take. No, it's like n u n minus 1 but multiplied by the variation of the internal function. You know that, for example, we have g of f is equal to g of x ka whole power n. You say na df by dx is equal to n g of x to the power n minus 1 g dash of x. Is similar to that one. Okay, but here we are using some different concept like variation. There in differential calculus, it's different differentiation. Here in variation calculus, it's like this. And here I want to mention here where n is an integer. Where n is integer. Where n is integer. And variation of summation of two functions u plus v is equal to the variation of the individual functions. Okay, and variation of function multiplied by x u is equal to x, we will take outside variation of u. Okay, these are the identities. And one more thing is we have, for example, we have differentiation is occurring like differential operator on some, then variation is you are operating variational operator or some function u. We can take the variation outside, put the differentiation inside du by dx. Okay, these are the some these identities. Also, for example, we have the variational operator occurring to be operated on some function which is given in like integral like this, definite integral x1 to x2. Function is some f of x multiplied by some another function u of x, and it is dx. We can easily write it as we can take the difference integration outside x1 to x2, a variation of internal functions, that's f of x, u of x, dx. Okay, which is equivalent to x1 to x2, since variation is only in u of x, because it's the function of unknown constants f of x, we can write the variation of u of x. These are very important identities because we will be using it. Okay, using all these identities we can prove, using above identities we can prove that some function f of x multiplied by the variation of u, it is equal to variation of both the functions f of x plus u of f of x u of x. And we can also prove u of variation of u is equal to 1 by 2 variation of u square. So it's very easy. Like if you have to take the, for example, you have u square function sum, you have to take its variation. So variation of u square, I already told you, n is here n. So it will be twice u 2 minus 1 variation of u. Okay, so it will be, if we take this to this side, variation of u will be equal to variation of u. In fact, u 2 minus 1 will be, sorry, 2 minus 1 will be u power 1 u, it will be 1 half of variation of u square. That I have written here. U times variation of u is called 1 half of variation of u square. You can relate it from here. Okay. And one more thing we can prove is that, for example, you have differentiation like du by dx, then you have differentiation of d of variation of u with respect to x dx. You can write it as du by dx like same. Then you can take this variation outside of the differential operator, variation of du by dx. Okay, du by dx. Then you can again take this variation outside. It will become like this now. This if we put this like this whole to be equal to u, and this is delta u. Okay, it is same identity u delta u. So u delta u is equal to 1 half of delta u square. So we can write it is equal to, it is here. Okay, 1 half of delta u of whole square. Delta, what is u? U is equal to du by dx. Du by dx or whole square. I hope you people understood these identities. These are very important identities. Now, the boundary value problem that I already told you. I will give you a brief introduction about variational method. Then we will solve our numerical problem. So the boundary value problem that we took in the initial class was our our BVP boundary value problem is okay. Our boundary value problem is like it is like this: d2u by dx square minus sine pi of x is equal to 0. We have to find its approximate solution. Okay, like, and the boundary conditions that were given is u of 0 is equal to 0 and u of 1 is equal to 0. It's from the last class. Okay, now we have to solve this with variational calculus, variational method or Rayleigh-Ritz method. So what are the steps? You please keep that in mind. Steps. Okay, so first step is we will multiply both sides of this differential equation with the variation of u of x, because u of x is a primary variable or the field variable here. We have to, because we will be assuming approximate solution to this only, so that's why variation of this function we have to take. So, and we have to integrate it over the domain. So what is the first? Multiply both sides of boundary value problem with variation of u of x and integrate over the domain. Integrate over the domain. So how it looks? So domain is, please note that domain is 0 less than x less than 1. Okay. So over the domain, integrating it from 0 to 1, then writing our differential equation d2u by dx square. I'm doing everything step by step for you people. Sine pi of x multiplied by variation of u of x. Different integrated with respect to d of x should be equal to 0. So what is this? I already told you what is this whole thing. This is error over the whole domain. So what we are trying to do is we are telling that error over the whole domain should be equal to 0. So this equation we are taking, then we are minimizing. We will not be able to, obviously with the approximate solution, we will not be able to make the whole error 0, but we will be able to minimize the error. So what we will do is that after that we use integration by parts to yeah, what we will do, we will use integration by parts to reduce the order of the highest derivative. Highest derivative is d2u by dx square. Okay, order is second in the expression to lower the degree as possible. In this case, the first term involves the derivatives and thus integrating by parts. Okay, so this will go to this one. This will be 0 to 1 minus d2u by dx square multiplied by variation of u of x, then it will be minus 0 to 1 sine pi x variation of u of x dx is equal to 0. Okay, it is also dx. Okay, so we have term, this is term first, term second. Okay, I just simplified this integral for you people. So what we have to do is there is this term contains the highest order derivative. Okay, so we have to use a integration by parts to lower its order. Okay, so using integration by parts IBP on first term. Okay, term. Okay, What we will get? We will have first term 0 to 1 minus d2u by dx square, variation of u of x dx. Okay, it will be integration by parts. Okay, it will be minus time as variation of u different du by dx, because if you integrate d2u by dx, uh, I mean to say that once it will be du by dx from 0 to 1 x equal to 1, like this. Plus minus is already there, then it is minus 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 plus. Okay, then it will be variation of u, then d, sorry, I'm writing it wrong, so it will be, we have to follow it from, it will be from 0 to 1 we have to solve it. Okay, then this is minus minus plus, we have integral of 0 to 1. Hope you remember the formula. Then we have to take the differential of the first function, d delta u of x by dx, and we have to use the du by dx function there, du by dx there, whole dx, because we know na u v dx is equal to, then we take v integral u dx minus integral of, we take dv by dx, u dx. Okay, it's like this, integral of d, integral of u dx. Okay, this formula, well, I have applied the same formula here. So after this, the complete equation will be like, I have to take these two things. Complete equation will be, if I add the second term as well, it will be minus delta u du by dx at x equals 1. So I am now splitting it, because it will be x at x equals 1 minus times at x equals 0. So it's minus already, it will be minus minus plus. So it will be delta u du by dx at x equals 0. Then we have this term plus integral 0 to 1. 0 to 1 we have d of delta u of x by dx du by dx. Okay, du by dx of dx. Okay, minus, we have this term. Okay, second term, this minus sin pi x delta ux dx. Okay, minus 0 to 1 sin pi x delta u of x dx, everything is equal to 0. So if I combine these two integrals, I will be getting minus delta u du by dx at x equals 1 plus delta u du by dx x equals 0, plus I will combine this integral 0 to 1. I will get d delta u of x by dx du by dx minus sin pi x sin pi x delta ux u of x, and this whole is under integral with respect to dx is equal to 0. Okay, then we have to further proceed like this. We have to use the mathematical manipulations to take the variation outside the integral. So the variation is existing throughout the integral. Variation is here, variation is here, variation is here, variation is here. We have to take this variation outside the integral. Third step. Okay, this was second step. Okay, third step is using identities, take variation outside of integral. Okay, taking outside of the integral. So what type of mathematical identity we will be using? I already told you just few minutes ago. D delta u of x by dx times du of x by dx. It's just a identity I wrote few minutes ago. Is equal to 1/2 of variation of du of x by dx का whole square. Du of x by dx का whole square. Okay, I wrote it right here. This. Okay, so we will be using this, and the second term of the integral. Second term of the integral. This integral. Second term is sine pi x delta u of x. So we can write it sine pi of x variation of u of x. We can write variation outside using the mathematical identity, variation of sine pi x u of x. Okay, so I can quote, let me write it as second equation, and this I wrote here as this first equation. It is same, no? F of x delta u is equal to delta times f of x u of x. Same I did it. F of x delta u of x delta times f of x sin x. Using first, using first, using second. Okay, so we can do the things like this. I will take this term. Okay, let me highlight it for you people. I am solving this term. Okay, this term of the integral. Okay, okay, inside term of the integral. So I'm taking that term only. So pasting it here is the same term. So how we can write it as? So first one we can write, this one we can write as equal to 1/2 of variation of, then we have bracket, this is du of x by dx whole square. If you compare it with the identity, it's exactly the same. And the second one minus variation of sine pi x u of x. Okay, I hope this is clear. And then I take variation from both of them common. Variation of 1/2 of du of x by dx over whole square minus sine pi x u of x. I hope this point is clear to you guys. Okay, so this term I can directly write substituting this. This is 1, 2, 3. This is 4. This is 3. Okay, okay. Substituting, substituting 4 into 3. So in place of this expression, we have to write this expression. So it will be minus del u du by dx at x, its value at x equals 1, plus del u du by dx, its value at x equals 0, plus I have to induce this term, variation of whole thing. This first we have integral 0 to 1, then we have to incorporate this term 1/2 of du by dx का whole square, dx का whole square minus sin pi x u of x. Then this is, sorry, I have to write it a little bit to accommodate everything. Sine pi x u of x, then it will be with respect to dx and its variation whole equal to 0. Okay, so now for these two terms we have to use the boundary conditions. Okay, fourth step is use boundary conditions to simplify boundary terms. Okay, look, these are the boundary terms because its solution at x equals 1 and x equals 0, it is a domain boundary. So what is the goal of this is that the goal of this simplification is that entire equation should be written as, when we use boundary conditions on these boundary terms, so we should have then variation of some whole thing should be equal to 0. This is our goal. Okay, we have to write this. This is our goal, to write the above expression, this expression, in terms of this. Okay, so if we see that boundary conditions like at x equals 0, we assume that, for example, I mean to say that at x equals 0, u of x is equal to 0, and x equals 1, u of 1 is equal to 0. We assume the variation of these functions at boundary terms is also equal to 0. That is, delta u is equal to 0, delta u1 is equal to 0. That's why we can just cancel these terms. X at x equals 1 is equal to 0, at x equals 0 it's also equal to 0. So our whole term simplifies to this term only. So our goal was to write it as a variation of something. So we are getting the same thing here. Okay, so finally we are getting something like this: variation of integral of over the domain 0 to 1. We have this dou u of x by dx over whole square minus sine pi x u of x. This is this. Okay, then it is dx equals 0. So this is our final expression. We have to do all the things on this expression to get the value of unknown constants a1 and a2. Okay, what we denote this inside quantity, this whole inside quantity we denote it by I of u. Look, it's a function of u only, so we write it as I of u. We called it as functional, denote by this. Okay, so we have finally arrived at something like this: functional variation of functional is a function of u is equal to 0. Okay, where functional I of u, okay, is equal to something like this. It is this term only. It is this term. Okay, it is this functional. So we got something new here, like this. Then we have to proceed. Okay, then we have to variation of functional should be equal to 0. We will get an equation with this, with the help of this, to get the value of a2 and a2. Also, from the last class, I had assumed that u of x to be equal to a naught plus a1x plus a2x square. Okay, last class. Okay, last class. Yeah, equal to x square. Then u of 0 equals 0, u of 1 equals 0. From that we got a naught to be equal to 0 and a1 equals minus a2. When we incorporate all these things into this, we get u of x to be simply equal to a2 times minus x plus x square. Okay, this is from the last class. Okay, then this u of x is like this. Its variation will be given as delta u of x is equal to variation of only one parameter, delta a2. Okay, delta a2 minus x plus x square. Okay, if you also see that if you put x equals 0 and x equals 1, you will get variation of u at x equals 0 also equal to 0, and variation of u at x equals, sorry, this gives variation of u at x equals 0 and variation of u at x equals 1 equals 0. So for example, if you put 0 here, 0, 0, it's multiplied by 0 is equal to 0. And if you put 1 here, minus 1 plus 1 equals 0, variation of u at x equals 1 is equal to 0. So it's satisfying this boundary terms, like we assumed variation of u is equal to 0 and variation of u of 1 is equal to 0. So boundary terms are vanishing initially like this here and here. So our functional will be then again the same thing. Functional will be like here again. So it is satisfying our assumption on boundary terms. So therefore our total functional I of u is again the same thing that we wrote it already. 0 to 1, 1 by 2 of du of x by dx over whole square minus sine pi of x u of x close dx is equal okay, this is functional only. Okay, so we will put all our things here. Okay, 0 to 1, 1 by 2. What is the value of du of x by dx? Okay, u of x is this, u dash of x will be a2 minus 1 plus 2x, isn't it? So we have to put it here, a2 minus 1 plus 2x. Okay, whole square. Okay, this is whole square here, minus sine pi x is at it is, we cannot do anything with it, and u of x is a2 times minus x plus x square. Okay, whole integral with respect to dx. Okay, if you solve this integral, it comes out to be, putting the values at x equals 0 and x equals 1, it comes out to be a2 square by 6 plus 4a2 by pi cube. I'm not solving this whole integral because it's only function of x and you have to put x equals 0 and x equals 1. You can solve these integrals in MATLAB or Mathematica, complex integrals. Okay, MATLAB or any other software. So functional, you can see that to what simpler degree this functional has been reduced to this. Okay, so now we have to minimize this functional to get the value of a2. So for that minimization, the stationary condition will be minimization stationary condition, stationarity condition will be variation of, we have to take variation of I of u is equal to 0, because this is our problem formulation. It means that for its variation to be equal to 0, it is partial derivative with respect to the unknown constants dou a2 should be equal to 0. If we take its partial derivative dou I by dou a2, it is equal to twice a2 by 6 plus 4 by pi cube, isn't it? So we have to put this here. It should be equal to, that is a2 by 3 plus 4 by pi cube should be equal to 0, or our a2 constant is equal to minus 12 by pi cube. I hope you understood that from where we got this a2. And in already I mentioned that a1 is equal to a2. So our a1 will be equal to 12 by pi cube. A1 is this, A2 is this, and A naught is equal to 0. So our solution to our differential equation, approximated solution, is equal to u of x is equal to 12, that is A2, 12 by pi cube x minus x square. So this is the approximate solution using Rayleigh-Ritz method. Okay. If you remember in last class, we got the same solution using Galerkin method. Wait, week 2, this is week 2. Galerkin method, we solved it with the help of Galerkin method, collocation method. This is Galerkin method. We got the same solution, 12 by pi cube x minus x square. We are getting the same solution here. Okay. I hope you people got the concept of Rayleigh-Ritz method. That is, this is actually the Rayleigh-Ritz minimization principle method. We use this to find the solution of our different approximate solution of our differential equation, or the boundary value problem using variational calculus. What we do is that first we assume the admissible polynomial as a solution that will satisfy that satisfies the boundary conditions. After that, what we do is that we induce the variation in the unknown constants that's there present in the approximate solution, that is a naught, a1, a2, and then we use the mathematical identities to boil down our differential equation or the boundary value problem to a simple expression that is we call as functional, so that we can write the whole differential equation as variation of some functional I of u is equal to 0. Then we have to minimize this thing only, that is the variation of I of u is equal to 0. It will be only 0 when it is partial derivative with respect to the unknown constants is equal to 0. We equated the same thing, partial derivative with respect to 0, we got a2 and then a1. Similarly, you can use the higher order polynomial, so the number of constants to be found will be more, and the number of equations will also be more. I hope you got this concept clearly. Thank you so much. Thank you everyone for joining this session. If you people have any question, you can ask.
Thank you for the session.
Thank you. If you people don't have any questions, you can leave. And next Saturday it will be conducted at the same time, 3 to 4. Initially I will be, then there is one more hour for the doubt solving. If you don't have any doubts, you people can leave. And in the next class, if you have any doubts at your assignment problems as well, you can bring those also. And in the next class, we will be starting the actual finite element method. That is the bar formulation for the bar and all, elementals, shear functions and all. This was very necessary because from this thing you got to know that how we develop element equations and other things using these approximate solutions, approximate methods.
Right, right.
Thank you.